I want to talk in this video about systems of nonlinear equations. Okay, now this would be a gigantic, endless topic. Okay, we're going to take a rather limited sample of systems of nonlinear equations. Okay, we're going to take some simple systems that we can solve either using the substitution method and or the elimination method. Okay. Alrighty, let's take a few simple examples here then, and let's take a look. So these are similar to the problems that have been assigned in the homework. Suppose I have the following system of linear equations. One's linear, one's not, okay? So when they say nonlinear equations, I should mention that doesn't mean necessarily all of the equations are nonlinear. This is actually a linear equation, as you can see. X plus y equals 4. If you graph that using Desmos or whatever, okay, you can see that would be a line. Okay? What is this creature? Is the set of all points x, y. Okay? Such that the sum of the squares of x and y is 9. This would be a circle. Okay? So you could see a line intersecting a circle. Now, speaking geometrically, you could see there might be what? No real solutions at all. Okay? Or there might be what? One solution where the line is actually tangent to the circle. Okay, you might consider that a double solution. That might be a good way to think of it. But another situation is where what? The line actually crosses the circle and you've got two distinct points of solution here. Okay, so you can already see what's going to be ahead here. Okay, let's use a substitution method here. Now I did the following. You could do it slightly differently, but I solved for y in terms of x using the first equation, the linear one. You can see if x plus y is 4, that implies that y is 4 minus x. Okay, so in the second equation, you can see what I've done with parentheses here. When instead of x squared plus y squared is 9, I have x squared plus 4 minus x squared is 9. Don't forget your parentheses. Okay, that sounds cool. Okay, let's expand these. This actually becomes x squared plus 16 minus 8x plus x squared is 9. Okay, 2x squared minus 8x plus 7 is 0 when that quadratic equation is rewritten in standard form. Here I went ahead and just used the quadratic formula on it, and I found that there are two solutions. Okay, so this will correspond to 2 points. X equals 4 plus minus the square root of 2 all over 2. Okay, I'm not going to go through the details of that. You should try it yourself and see that you get the same thing. Now, remember that we need the corresponding values of y here. Y is always what? 4 minus x. Okay? Now, I'm doing this in a shorthand way. Okay, so I'm not writing them separately. I'm just going to go 4, which is actually 8 halves, minus 4 plus minus the square root of 2 over 2. Okay? Alrighty? So that's going to be the same thing. So I'm doing 2 at once, really. Okay? And you can see here, you're just going to use the distributive property because I've got what? A common denominator. And that's 8 minus 4 is 4. Okay? But that negative sign distributes through the plus minus and becomes minus plus. Okay, so I've got minus plus the square root of 2 over 2. So what this is saying here is if I've got a plus up for my x value, I've got a corresponding minus value for the y value. Likewise, if I have a minus, 4 minus the square root of 2 up here, for the x value, I actually have what? Plus for the y value here. Okay, now, so the 2 points of intersection, okay, so there's only 2 points of intersection. 4 plus the square root of 2 over 2, comma 4 minus square root of 2 over 2. Okay, see these sign change. And then what? X could be 4 minus the square root of 2 over 2, in which case y is 4 plus the square root of 2 all over 2. I should be saying all over 2, shouldn't I? Okay, all right. Now you could graph these on Desmos or something and you could actually double check yourself. Okay, that might not be a bad thing to do. Let's use a different method here. Let's take a system of equations where we can use the elimination method to solve it. Okay. All right, we've got x squared plus y squared is 25. That's what? A circle of radius 5 centered at the origin. And we've got x squared minus y squared, okay? That is actually a certain hyperbola, okay, of two branches here. So we could have, no intersection, no real intersection points, 2 intersection points, 4 intersection points. I say that because these actually all have centers at 0, 0. So you couldn't have just 3 or something. But other situations you could. Anyway, let's keep going. All right, here's what I'm going to do. I'm just going to add these two. Doesn't that look like a straightforward thing to do? Notice that the y squareds, it just end up canceling if I add it just straight down. And I've got 2x squared is what? 25 and 1 is 26. Taking halves and then taking square roots. I've got two possibilities for my x, plus or minus the square root of 13. Okay, now I'm going to back substitute again, and here I'm taking two cases at once like I did above. Okay, I decided to you could use either equation to solve for the y. I'm going to use the first equation for no particular reason. We've got x squared plus y squared is 25, so I've got plus or minus the square root of 13 squared plus y squared is 25. Plus or minus the square root of 13 squared is still always positive 13. So we've got 13 plus y squared is 25. Y squared is 12. So y is plus or minus the square root of 12. Factoring out the square root of 4, which is 2, we've got plus or minus 2, the square root of 3. Now you understand here there's actually 4 points, right? Because what? For each x value here, I actually had 2 corresponding values here, and 2 times 2 is 4. So the solutions are square root of 13, 2 square root of 3, okay? Square root of 13 minus 2 square root of 3, minus square root of 13, 2 square root of 3, and then minus square root of 13 minus 2 square root of 3. Again, graphing these might be a good idea, okay? It can help you see what's going on in many of these situations. Alrighty? Let's do one more here, okay? I'm actually going to use a substitution method here, okay, rather than elimination. You could actually use an elimination method also, but I'm going to use a substitution method. Now, the reason I'm choosing this also is to show you that there's good substitutions and there's poor substitutions. All right, let's come up here. One might think about doing this. You notice that y is explicitly in terms of x in the second equation. Y equals 20x squared minus 1. You might think, therefore, of doing what? Replacing y by 20x squared minus 1 in the first equation and getting x squared plus the quantity 20x squared minus 1 squared equals 1. Now, just to contemplate that for a minute. And it is doable this way, okay? It is doable this way, but do you see that you're going to get a fourth degree polynomial? Okay? It's actually going to be a fourth degree polynomial of this form. Ax squared plus bx squared plus c equals 0. So you don't need the quartic formula or anything. You can actually use the quadratic formula with a simple substitution. But it's not going to, you can see that this is probably not going to be the easiest approach. Another thing that sometimes happens in some of these, you get something called extraneous solutions. If you remember back when we were solving some equations here, when you square both sides of an equation or raise each side of an equation to an even power, even though the originals are equal, well, you might get extra solutions because just because the squares are equal doesn't mean the originals were equal. So you might actually get extraneous solutions doing it that way. I don't know. I didn't do it that way, so I'm not going to touch that. Okay, that's just conceivable in some situations that that might happen. Can you think of a different substitution to use instead? Well, here's what I thought about, because I don't want to creep up to a fourth degree polynomial. How about I use a substitution method for x squared here, in either one? I'll show you what I did. Okay? How about we solve for x squared instead and then substitute in one or the other? So this is what I did. Because x squared plus y squared is 1, I could actually say this. X squared is 1 minus y squared. And then I've got what? Y equals 20x squared minus 1 becomes 20 times the quantity 1 minus y squared minus 1. Okay, use the distributive property and rewrite everything, and we get the following quadratic equation. Just a simple quadratic. Hooray! No fourth degree here. 20y squared plus y minus 19 is 0. I think you can see pretty quickly that this is going to be solvable without the quadratic formula. Try factoring first whenever you run into a quadratic equation. Okay, and I did here. I found it's 20y minus 19 times y plus 1. So that means y is 19/20ths, or y could be what? -1. Taking each factor, setting it to 0, and solving. Okay, let's consider this situation where y is 19 out of 20. Okay, going back to the second equation where y equals 20x squared minus 1. Okay, I've got 19/20ths is 20x squared minus 1. I add 1 on each side and get 39/20ths equals 20x squared. Divide both sides by 20, and the denominator becomes 20 squared. And take in square roots, okay? And don't forget, get rid of absolute values, plus minus, right? Plus minus the square root of 39 over 20. Okay, so that's what x would be corresponding to that particular y values. So we have 2 points, right? If we were to think geometrically, we've got 2 pairs of solutions already, or 2 points in common between these 2 curves, okay? All right. How about the case where y equals -1? We've got x squared plus -1 squared is 1, so I used the first equation this time. You could have used the second. That means x squared is 0, right? Means x equals 0. Okay? Some people might consider this a double 0. Okay? Multiplicity 2. There's a reason for that. These actually, if you actually graph these on Desmos, the curves are actually cotangent at that point. 0, -1. Okay? Anyway, so here's our solutions. Square root of 39 over 20, comma, the y value 19/20ths, or what? Negative square root of 39 over 20, comma, 19/20ths, or the point 0, comma, -1, which some people might justly write twice. Anyways, I hope this helped with some of the problems in that section. Okay? They shouldn't be too hard. All of them should be quite doable. Alrighty? All right, signing out.